All right, continuing on with conditional probability and now the multiplication rule. Multiplication rule says the probability that A and B happens is the probability that A happens times the probability that B happens given that A has already occurred. So defective batteries. We have 4 good batteries and 6 dead batteries in a drawer. They are mixed and visually indistinguishable. Suppose you randomly select batteries from the drawer without replacement. Simply means when you pick the first battery out, you don't put it back in before you take out the second battery, which would make sense. So find the probability that you get a good battery on the first pick and a bad battery on the second pick. So the probability you get the first is good and the second is bad. An and is just the right word to use here. I mean, it's not, well, even I guess I said it right here. It's not an or problem, it's an and problem. So that's a multiplication rule. What's the probability the first is good times the probability that the second is bad given the first is good. Oh. Okay. So the probability that the first battery is good. Well, there's a total of 10 batteries, and 4 of them are good. So that is 4 out of 10 times. Now, what's the probability the second battery is going to be bad, given that you picked out a good one on the first pick, and you don't replace it? So instead of 10 batteries in the basket in the drawer, now there's going to be 9 batteries total. And of those 9 batteries, 6 of them are bad. So there it is. We could reduce it down and whatever else, I guess, but who cares? It's just, well, it's easier just to reduce it. Take a 3 out of this, take a 3 out of this, take a 2 out of this, take a 2 out of this. So that would be 4 out of 15. Also known as, sorry, I'll type it in when the calculator gets booted up. But that, or why even just leave it? That's fine. You don't need to put decimal approximations down. Part B, find the probability that you get 1 good battery and 1 battery when you pick 2. Okay, so this is different than the first one. For the first one, I had to get a good one on the first pick and a bad one on the second one. This one just says you got to get a good and then you got to get a bad. Doesn't really matter what order you get them in, okay? Okay, that's bothering me. I'm sorry. I got to type it in to see what the 4 out of 15. The reason I like to see these decimals, 2, 2, 6, 7, because when I see the decimal like this, I know it's 27%. It gives me a frame of, it gives me some understanding about how likely it is for it to happen. Whereas I see 4/15, it doesn't quite click for me. Regardless, for the next one, so this is a probability. So there's 2 ways that we can get a good and 1 bad. We can get a good first and a bad second, which we just calculated, or we could get a bad first and a good second. So this is a combination of an and, which is a multiplication problem, and an or, which is an addition. So I'm going to say first good and second bad, or first bad and second good. So this is, kind of a complex problem. This is basically what I calculated all right here. And then this is another and problem, and I combine them by using an or problem. Remember, or problem is an addition rule. And in this case, these are mutually exclusive events. Like you can't get, if the first one's good and the second one's bad, that's mutually exclusive to the first one being bad and the second one's good. They can't happen together because, so I don't really need to break it down quite like this. Let's just use the multiplication rule in conjunction with the addition rule. So the first one is good. Well, that's 4 good batteries out of 10 times. What's the probability the second's bad given the first is good? Well, now there's 9 batteries and there's 6 good ones. Or plus, what's the probability the first one is bad? Well, there's 6 bad batteries out of a total of 10 times. If the first one is bad, what's the probability the second one is good? Well, now there's 9 batteries left over, and there are 4 good ones left. So as you can see, it's this times this. And I'll just point out to you that these do have the same value. 4 times 6 divided by 90, and then 6 times 4 divided by 90. So basically, it's just that 4/15 that I calculated before times 2, which gives me basically 8 6/15, which is twice as big as this, but I'm just going to type it in so I don't have to think about it. 5333. So the probability of getting one good and one bad is over 50%. That'll happen over half the time. Okay? But it could happen in two different ways. Find the probability that you get 3 bad batteries in a row. So this is a probability that you get the first is bad, and the second is bad, and the third is bad. So kind of tempted to kind of write this out. This is just the multiplication rule with a sequence of 3 consecutive things. So this is going to be the probability that the first is bad times the probability that the second is bad given the first was bad times the probability that the third is bad given the first and second were both bad. But we don't have to write it like that. It's just multiply them out. First is bad. There are 6 bad and 10 good. 10 total. So 6 bad out of 10 times. Once you take that bad battery out of the basket, there's only 5 bad ones left over and 9 total left over. Times. Now I've taken out 2 bad batteries. So now there's only 4 left over and a total of 8. So the multiplication rule can be very easy to implement if you just kind of think of it like that. So 6, 5, 4, 10, 9, 8. 6, 5, 4, 10, 9, 8. And we could have cleaned it up a little bit by ourselves, but 1, 6. 167. 0.167. So there's only about a 17% chance that if I pick 3 batteries out, all 3 of them would be bad. And by the way, the reason this was so easy to calculate is because there's only one way for it to happen. You have to get a bad and a bad and a bad together. When we start doing combinations of 2 bad and 1 good, now you got to look at all the different ways that you can get that combination, which is this last problem. Find the probability you get 2 good batteries when you pick 3. So this is a probability that you get a... So I'm going to shorten up my notation again. What I really want to say is the probability that I get the first is good and the second is good and the third is bad, or... But I'm just going to kind of go, I'm going to kind of write the ands, I'm going to write this as the probability of bad, bad, bad. So I'm going to skip the and to shorten it up. So this is a probability that the first is good and the second is good and the third is bad, or I get a good, bad, good, or I get a bad, good, good. So the idea here is there's 3 different ways to get 2 good batteries in 3. There's 3 different orders that I can get them in. So these are each an and. So the first one's a good, so there's 4 goods. So good out of 10, 4 out of 10, times. Now I've taken 1 good one out. This is a probability that the second one is good, given the first one is good. So that's going to be 3 good ones left over, 9 total left over, times bad, there are 6. So the last one, there's still 6 bad, and now there's only 8 left in the drawer. Or, plus. Thankfully, these are all mutually exclusive. They can't happen together because they're different combinations. So this is the probability that the first one is good. That's 4 good out of 10 times a bad, 6 out of 9 because one less left over, times the third one is good. So I had 4 good ones, now I got 3 good ones. I had 9 total, now I got 8 total. And plus. The first one's bad, 6 out of 10. Second one's good, 4 out of 9. Last one is good, 3 out of 8. And again, notice these 3 sets of, these 3 expressions, these 3 products are all exactly the same. 3 times 4 times 6, and 10 times 9 times 8. So basically it's just 3 times one of these. So to calculate that, I'm going to type it in like that. So I have 3 times 3 times. So on the top, I'm going to go 4, 3, 6, and then 10, 9, 8. 4, 3, 6, 10, 9, 8. Control Enter. 30%. All that for just a measly 30%. So there's a 30% chance that I'll get 2 good batteries and 1 bad. Okay? So now if you're looking at this and saying, well, that's all pretty easy. Well, it's pretty easy when, in my opinion, it's pretty easy when somebody else does it. But it's really something that you need to practice. It helps to write notation. You got to show your work. That's all stuff that is expected on the AP test. I've got about 4 minutes. Let's do one more example. Playing in the NCAA. About 55% of high school students play a sport while they're in high school, and about 5% of these athletes go on to play on a college team in the NCAA. Find the probability that a randomly selected high school student plays sports in high school and plays on an NCAA college team. Okay, so if you're like me, when you read that, you're just like, okay, what? You see these numbers, and you're like, I got to do something with those numbers, but I'm not real sure what. And you start thinking, well, maybe I'll multiply, maybe I'll divide. I would encourage you whenever this happens to start putting stuff down in probability notation so that we can use our formulas if we want to. Find the probability that a randomly selected high school student plays sports in high school and so I need to find the probability that they are a high school athlete and NCAA athlete. So I want the probability that they both happen. All right, so what is this 55%? 55% of high school students play sports. So this is a probability that you are a high school athlete. That's 0.55. So what is this 5%? About 5% of these athletes go on to play NCAA sports. So this is not the probability that you are an NCAA player. It's just not. It's of the high school athletes. So given that you're a high school athlete, 5% play NCAA. So this is NCAA given that you're a high school athlete. Okay, so I guess they're giving me these two things. They're giving me exactly what I need. An and is a probability that you're a high school athlete times a probability you play NCAA given you're a high school athlete. So you might say, well, I was thinking I should just multiply them. Well, this is 0.5, sorry. Well, if you are confident that you should just multiply them, then you go right ahead. But here's the deal. You don't always just multiply the numbers that you get, So I would encourage you to 0.275. I would encourage you to really set up the problem, write down the given statements that they're giving us in probability notation, think about exactly what you want to find, and start putting the pieces together so that you know multiplying is the way to go on this one, okay?